This is practice problem number 5 from Lesson 1, Number Puzzles, and Unit 4, Linear Equations and Linear Systems. And this is a revised version of practice problem number 5. In problem number 5, a store is designing a space for rows of nested shopping carts. Each row has a starting cart that is 4 feet long, followed by the nested carts. So 0 nested carts means there's just the starting cart. The store measured a row of 13 nested carts, so 13 nested carts, to be 23.5 feet long, and a row of 18 nested carts to be 31 feet long. These are nested carts. So this first cart is 4 feet long, and that is with 0 nested carts. And each cart after that adds, and you're going to see this calculation in a moment, adds 1.5 feet. So 0 nested carts gets you out 4 feet from this wall here. So here's the wall, and this first cart goes out to this point right here. That's 4 feet. And then each nested cart that's added after that adds 1.5 feet. So this is 1.5 foot more. This is 1 nested cart. 1.5 feet more. This is 2 nested carts. So this calculation, how do I get this calculation of 1.5 feet? That is a 1.5 foot change for every nested cart that's added. So this is building the idea of slope or change for each unit along the x-axis, or in this case, each cart. I can calculate this 1.5 foot increase by noticing that if I increase the number of carts by 5, so the number of nested carts by 5, so if I go from 13 nested carts to 18 nested carts, that's a 5 nested cart increase. Notice that the number of feet increases by 7.5. So if I increase 7.5 feet for 5 carts, that means each cart is increasing the number of feet by 1.5 feet. So I have a 1.5 foot increase per nested cart. So 1.5 feet increase for each nested cart. So 1.5 feet, 1.5 feet, 1.5 feet, and so on. So that is a calculation of slope. So how much change is there in the vertical direction or along the y-axis for every unit change in the horizontal direction or along the x-axis? So how many feet increase is there for each nested cart? So this is the vertical change, the number of feet. This is the horizontal change, the number of carts. This is y and this is x. And so there's a 1.5 foot increase for each nested cart. That's 7.5 feet divided by 5 feet. So this is a really nice example of using 2 points on the graph to calculate slope. And you can actually see it. I've increased the number of nested carts by 5. I've increased the number of feet by 7.5. So that is a 1.5 foot increase for each nested cart. To graph this relationship of nested carts to number of feet, I labeled the x-axis number of nested carts, and each grid line is 2 nested carts. I want to get out to 20. If I labeled each one of these 1 nested cart, the graph would be way off to the right. And I have to get to 18 because that's a number of nested carts given, so I want to go out to 20. And I know that later on, it turns out that I have to go out farther than that. The number of feet, I know that there's a 1.5 foot increase for each nested cart. So 1 nested cart increases 1.5 feet. That means the 2 nested carts increases 3 feet. So 2 nested carts increase 3 feet. 2 nested carts increase 3 feet. So I counted by 3 feet for each grid line going up. So I know at 0 nested carts, so that's the starting cart only, I'm 4 feet from the wall. So 0 nested carts, I'm out 4 feet. For 13 nested carts out here, I know I'm at 23.5 feet because that's what's given in the problem. And for 18 nested carts, I'm at 31 feet out here, so 31 feet from the wall. Connect these points, get the straight line, and on the graph, every 2 carts, this is 1 foot above the grid line. So 2 carts, this is 1 foot above the grid line because it increases 3 feet. So I'm starting out 1 foot above the grid line, so the 4 feet, it's 1 foot above 3 feet. So this goes out 2 carts, increase 3 feet. So this is 7, this is 10, This is 13, this is 16, 19, and so on. So 1 foot above the grid line. It's useful when we get out here because we're going to have to look at a number of feet and a number of carts out here in a few moments. So the slope is calculated as the change along the y-axis, or the change in the vertical length. So that says 31 minus 23.5. So 31 minus 23.5 is a 7.5 foot change in the vertical direction, starting at 13 nested carts and going to 18 nested carts. That's 18 minus 13. So that's for 5 nested carts. And so how much is that for each nested cart? That's the slope. How much change is there for each unit or each nested cart? Well, there's a 1.5 foot increase for each nested cart. That is the slope of this graph. So feet increase 1.5 feet for every 1 nested cart added to the row. So add a nested cart to the row, increase 1.5 feet. Add another nested cart to the row, increase another 1.5 feet. Add 2 nested carts, increase 3 feet. So 2 nested carts, increase 3 feet. 2 nested carts, increase 3 feet. Now looking ahead, I know that they're going to ask me how many carts can I get in a space that's 43 feet long. So I'm going to go out here to 43 feet. So this is where it's useful to know that the number of feet is 1 foot more than the grid line. So this is 42. So 1 more is going to be 43. And so if I extend this line, it does go through this point. So this is 43 feet. And we can also write the equation for this line now. So this is y equals mx plus b. So that's the slope-intercept form of the equation. We know that the y-intercept is 4 feet. It's down here. So if I have 0 carts, I'm at 4 feet. So this is where the graph intersects the y-axis at 4 feet. And we know that the slope, we just calculated it, is 1.5 feet for each cart. So this slope right here is 1.5. That's 1.5 feet for each cart. Now if I go out here to 43 feet, it looks like that's going to be equal to 26 nested carts. So let's replace x with 26 nested carts and see what we get. So 26 nested carts times 1.5 is actually 39. And 39 feet plus the 4 feet from the starting cart, that adds up to 43 feet. So y, the number of feet in the space, is 43 feet for 26 nested carts plus 1 starting cart. So that's going to be a total of 27 carts. So now this point is 26 nested carts for 43 feet. So there are 4 ways to think about these problems. One is this graph, and this graph starts at 4 feet because that's the starting cart, and then each nested cart that gets added on increases the length of those carts by 1.5 feet. So the number of nested carts, as that number increases, the number of feet increase by 1.5 feet per cart. A second way is the equation. And so now we know that the carts start at 4 feet, and each nested cart adds 1.5 feet. So the total number of feet is the number of nested carts times 1.5 feet per nested cart plus this 4 feet in the beginning. So now we know if you go out 26 nested carts, you will have a total of 43 feet. That includes the 1 starting cart right here at 4 feet. A third way to think about this problem is using a drawing, which is always a good place to start. So we have a starting cart, which gets you out 4 feet from the wall. So cart 0, which is the starting cart, equals 4 feet. And every nested cart after that adds 1.5 feet to the length. That is the slope, 1.5 feet for every nested cart. So each nested cart adds 1.5 feet to the row. 1.5 is the slope of the line. The slope equals the change in feet. So every nested cart adds 1.5 feet. So for each unit x, so 1 unit x is 1 nested cart. So the more you look at the drawing, and then you look at the graph, and you look at the equation, and you look at all 3 of those together, the more you will understand the problem. Go back and forth and think about it each time. Another way to think about this problem is by reasoning through it. So you have 43 feet of space to fill. The starting cart, or 0 nested carts, takes up 4 feet. So you subtract that 4 feet from 43 feet, so you have 39 feet left. And each nested cart takes 1.5 feet. So how many of these 1.5 feet are there in 39? That's like saying how many of these nested carts are in 39 feet. So divide 39 feet by 1.5 feet for each cart, and that equals 26 total carts. Now this division right here, 39 feet by 1.5 feet, it's useful to think of these problems as fractions. So 39 divided by 1.5 is the same as 39 divided by 3 halves. So 1.5 is the same as 3 halves. Once you do this, and once you get used to it, you can do this calculation in your head faster than you can use a calculator. So there are a couple ways to solve this 39 divided by 3 halves. One way is to multiply 39 by the multiplicative inverse of 3 halves. So 39 times 2/3. The reason that works is 3 halves times its multiplicative inverse is equal to 1. So this goes away. This becomes 1, and you're left with 39 times 2/3. So 39 divided by 3 is 13, and you want 2 of those thirds, or 2 of those 13s. So 2 13s is equal to 26. The same 26 is over here. Another way to look at this division is to think of 39 divided by 3 halves as saying how many halves are there in 39? So how many of these halves are there? So it's 2 times 39. This 2 times 1/2 right here, this goes away, and you're left with 78, and you're going to take those halves out 3 at a time. So 78 divided by 3 is 26. Not spending a lot of time on this, but it's useful to look at decimal values, easy decimal values, as fractions, and try to do the calculation in your head. So we have to add this one last cart, the beginning cart, so that gives us 27 total carts. So let's go back to the equation. So the number of total feet is y total feet. The slope, the number of feet added for each cart, is m. The number of nested carts is x, and the starting cart is 4 feet. So you're given 43 total feet. You know that each nested cart takes 1.5 feet. So how many of those nested carts can you get into that space with a starting cart taking up 4 feet? So you subtract the starting cart. So 43 minus 4, or 43 plus a negative 4 equals 39 feet. And that is equal to the total number of nested carts times 1.5. Multiply by the multiplicative inverse of 1.5, which is 1 over 1.5. 39 times 1 over 1.5, or 39 divided by 1.5, is equal to x number of nested carts, which is 26 nested carts. Add the 1 starting cart, and you're left with 27 total carts. The goal of the course is to learn this algebra, but it's really important to understand that algebra as you go through the course. That understanding comes from reasoning about the problem, from graphing the problem, from making drawings of the problem, and of course, working through the equations for the problem. So all 4 ways that we've discussed help in a better understanding of the algebra.